Hello students, welcome to your physics class. So today I am going to start lectures on a very important topic from your module on optics. The topic that I am going to discuss beginning from today is polarization. Polarization of light. So this is the topic of our lecture. And here on your screen is a very beautiful picture which is an example of polarization of light occurring in nature. This is basically a picture of the evening sky just before sunset. So if you look at the time of capture of these photographs, they are at 6:30 p.m. and 6:50 p.m. respectively. So it's a picture of the evening sky just before the sun sets. And in order to capture these photographs, we have used a lens which can detect the effect of polarization of light. So these pictures are basically depiction of polarization of light in evening sky. So what is polarization of light and how can the effect of polarization of light be captured? These are things which we are going to understand through our series of lectures on polarization. Now, before I begin the actual lecture, there are a couple of very quick questions for you. First question, what are the natures of light wave and sound wave? So you have 4 options. Please choose the correct one. Next question, which of the following is not an electromagnetic wave? Again, you have 4 options and you have to choose the correct one. So before I begin my actual lecture, let me tell you the points that I intend to cover through my lecture series. Firstly, I want to understand with you what is polarization of light or what is polarized light. Next, we will understand how can polarization be brought about through reflection. Next, we will understand how can polarization be brought about through refraction. Then we'll proceed to understand how light can be polarized through double refraction. Next, we would be understanding the working of a polarizer and an analyzer. Next, we would be speaking about uniaxial and biaxial crystals. Then we would proceed to understand Huygens' theory behind double refraction of light. Then we would see how Nichols prism can be used as a polarizer as well as an analyzer. Next, we would be understanding what are retardation plates and how they can be used to produce as well as detect various kinds of polarized light. Next, we would go into detection of various kinds of polarized light using an analyzer and a retardation plate. And finally, we would conduct an in-depth theoretical analysis for production of light having various kinds of polarization. Linearly polarized light, circularly polarized light, elliptically polarized light, and so on. First and foremost, beginning from the very beginning, what is polarization of light? Now, as we all know that light is an electromagnetic wave. It is constituted by electric field vectors and magnetic field vectors which are vibrating mutually perpendicular to each other. And the direction of propagation of light is perpendicular both to the direction of vibration of the electric vector and the magnetic vector. So basically the electric vector, the magnetic vector, and the direction of propagation of light, they three are mutually perpendicular to each other, light being an electromagnetic wave. Now, from now on, we will be calling the electric vector of light as light vector. So when I say light vector, you understand that I'm referring to the electric vector of light. Now, if for ordinary unpolarized light, if we have ordinary unpolarized light, then its electric vector, as we see from the first picture, its electric vector is free to vibrate in any direction perpendicular to the plane of propagation of light. So if light is propagating this way, say along the z-axis, this is my z-axis, say, then my light vector is free to vibrate in any direction along the xy plane. So the direction of my light vector varies arbitrarily in the xy plane if my light is propagating along the z direction if I have unpolarized light. But then if I manage to confine the direction of vibration of light vector in, suppose, the plane of your computer. So this is the xy plane. So it is free to vibrate along any direction in the xy plane. But if I am saying no, my light vector can only vibrate in a certain direction along your computer screen. So my light vectors can only vibrate this way if my light is propagating along z direction. So it is confined to your computer screen. So it can only vibrate in the direction which is formed by the intersection of the xy plane with your computer screen. So it can vibrate along this direction. So then I say, as I see from figure B, that I have been able to polarize light. I have been able to polarize light because I have confined the direction of vibration of its light vector. It is not free to arbitrarily vibrate in any direction along a plane, but it is confined to vibrate in a certain direction. So I have managed to polarize light. And in this case, the plane of polarization is the plane of your computer screen or wherever you're seeing the presentation, that screen. Because light vectors vibrate along that screen. And also, I could have confined the light vectors to vibrate perpendicular to that screen. Okay, so in the picture C, you see light vectors are vibrating perpendicular to the screen. So then the plane of polarization is perpendicular to your computer screen. So these two are examples of polarized light with plane of polarization along your computer screen or perpendicular to your computer screen. Now the arbitrariness in the direction of vibration of light vector is completely gone. And so I say now light is polarized. And the kind of polarization is known as plane polarization because I am confining the light vectors to a plane. Next, I'm going to tell you how can we bring about polarization of light through reflection. Okay, how can we polarize light through reflection? So what we have on screen is a 3D view, kind of 3D view of the phenomena, where we see that unpolarized light is coming in and being incident on this plane. Unpolarized light, you see the light wave vectors are vibrating in arbitrarily in all direction along the plane perpendicular to the direction of propagation of light. That unpolarized light is incident on this plane. But the reflected light for a certain special angle of incidence, which we are going to speak about, for a certain specific angle of incidence, the reflected light gets completely polarized. And here we have a two-dimensional view of the phenomena. Here you see that the light is incident at a particular angle of incidence, IP, which is known as the angle of polarization. And if it is incident at this special angle, the angle of polarization IP, then the reflected ray is getting completely polarized. And the angle between the reflected ray and the refracted ray is 90 degree for this special angle of incidence. If the angle of incidence is equal to the angle of polarization, then the reflected ray and the refracted ray are mutually perpendicular to each other and the reflected ray is completely polarized. So what is happening is the reflected ray is completely polarized, as I say, and in this particular picture we have said that the direction of polarization of reflected ray is perpendicular to the computer screen. So we have depicted it by dots because it's perpendicular to your computer screen. Okay, so we are partially cutting off from the refracted ray, we are partially cutting off all or most of the light that is having vibration which is perpendicular to the computer screen. That is being cut off. So the refracted ray in turn becomes partially polarized because it has less of light having vibration perpendicular to the computer screen and more of light having vibration along the computer screen. So it's having, the refracted ray is having a greater percentage of light having vibration parallel to the computer screen because most of the light having vibration perpendicular to the computer screen are going off in the reflected ray. So we are saying that the refracted ray is partially polarized in the process, but by reflection, the reflected ray is completely polarized. Next, we have the Brewster's law, which basically spells out this phenomena of polarization through reflection. So the Brewster's law states if the angle of incidence is the angle of polarization, then the reflected light will be plane polarized, and the angle between the reflected and refracted light is 90 degree, or they are mutually perpendicular. And here n is this is the mathematical statement of Brewster's law, which you see on your screen. And here n is the refractive index of the medium. So we know by Snell's law, the refractive index of the medium is sine of angle of incidence by sine of angle of refraction. The angle of incidence is, of course, the polarization angle, IP, and the angle of refraction is 90 degree minus IP. Why? Because the angle between the reflected light and the refracted light, they are mutually perpendicular. So the angle between reflected and refracted light is 90 degree. And we know the angle of incidence equal to angle of refraction. So angle of reflection. So if the angle of incidence is IP, then the angle of reflection is also IP. So the angle of refraction would be 90 degree minus IP, because the total angle along a straight line is 180 degree. So sine IP by sine angle of refraction reduces to sine IP by sine 90 degree minus IP, that is sine IP by cos IP, which is tan IP. So ultimately we get the relation that refractive index of the medium through which refraction is happening, that is equal to tan of the angle of polarization. So given the angle of polarization, you can find the refractive index of the medium. Given the refractive index of the medium, you can predict the angle of polarization.